Today we're going to talk about blood vasculature and the lymphatic vasculature. We want to look at the function of vessels, layers of the vascular walls. We want to classify the different types of vessels, capillaries, arteries, arterioles, venules, small veins. And also we look at the components in the wall of these and what makes them different. We want to look at the control of the microvasculature, talking about the arterioles as well as the shunts that go through and end up with a portal system. We want to look at the variation in that microvasculature. We want to look at the blood barriers, and we end up with some lymphatic system which collects fluid from the vasculature and transport it back to the blood vessels. Thank you. Here we see a picture of early blood transfusion. And in those days, before 1900, no one knew that the different types of blood should match before you transfer from one individual to another one. Now, multicellular animals need three mechanisms. One is to distribute oxygen, nutrients, and hormones. Two, to collect waste. And three, to transport waste to excretory organs. And the cardiovascular system meets those needs of multicellular animals to distribute, collect, and transport. And here we can see we have the heart and two sets of closed vessels. One goes to the lungs and back. The other one goes to the rest of the body, the systemic one does. And they join each other only at the heart. Here we see the heart and the blood vessels go into the various extremities as well as to various organs in the body. And again, we can see the heart, major vessels running down the legs and the arms, and how we have rich vasculature in the liver, in the heart, in the kidney, as well as in the face. And brain, of course, has a major blood vessels there. Now, if we look at the cardiovascular system, the main pressure producer is the heart. Whenever it contracts systole, it makes pressure. The elastic arteries collect blood and maintain pressure. Is what they do, and you can see the elastic arteries coming out of the heart, going to the pulmonary circulation or to the systemic circulation. Then there's muscular arteries, and they distribute blood and maintain pressure. And then we have arterioles, and they're responsible for peripheral resistance. They resist the pressure. So contraction of smooth muscle and blood vessels reduce the caliber and reduce the rate of flow. The arterioles resist the rate of flow in such that no longer is there a pulse. There's a pulse in elastic arteries, muscular arteries, arterioles, but no pulse occurs in the capillaries, which is the next one. And that's important for metabolic exchange for nutrients and waste. And then we have venules, which collect blood from the capillaries, and also the venules is a source of edema. You get stung by a bee, it swells up, is leaking at the venules. And then the veins carry blood back to the heart. And then also a large reservoir is in the veins. So a large amount of blood is stored in the vein. And finally, it returns the blood back to the heart and is a reservoir, as I mentioned to you, and we'll see in a minute. Now here we can see where the heart is contracting. The effect of contracting heart has on the pulse of the arteries. It's elastic arteries, and then arterioles, and through here. So we got elastic and then muscular and then arterioles, and it's still containing a pulse. And then when you get beyond the arterioles, you just have a steady flow of blood, a steady pressure of blood. It could be even negative in the vena cava. And here you can see the velocity of the blood changes with each of the heartbeat. And here we can see the area. The greatest area is the capillaries. In fact, you can't puncture your finger any place and not get blood because you'd be puncturing a capillary. And that illustrates that the capillary has the greatest surface area, and that's where you're going to have the metabolic exchange. Now, the blood vessels, these vessels here, have to be adapted to withstand the mechanical stress and make the metabolic needs. It's what we do. And arterioles is responsible for the peripheral resistance to take away the pulse from the blood and just have a continuous pressure or a continuous flow with the pressure. You don't have a pulse. And here we can see the different vessels. Here's the arteries, arterioles, capillaries, muscular venules, and then we back to veins, back to the heart. And so in order to withstand the mechanical factors, we need elastic tissue and a lot of muscle. And then as the mechanical factors get less, you reduce elastic tissue and also reduce the amount of muscle. And then you remove that muscle. When you need metabolic needs, that's where you have capillaries. And then when you come back into the larger vessels, going back to the heart, you increase some of the mechanical factors, and you even pick up some elastic tissue, and you have smooth muscle in the wall, even though it's not as much as you have in the arterial side. So to resist the pressure, the blood vessels are adapted for metabolic needs as well as mechanical factors that will be influenced by them. Now, if we look at elastic arteries, they conduct blood and maintain pressure during diastole when the heart is not contracting. So here you can see when the heart contracts, goes to 120 millimeters of mercury, and it increases that pressure in the aorta to that amount. And the aorta gives, it stretches. And then whenever the heart relaxes, it goes back to 2 millimeters of mercury from 120 to 2. And then you get a recall of the elastic tissue in the aorta, and that helps maintain the pressure. So you don't go to 120 to 2, you go to 120 to 100, like that. And here we can see elastic arteries with the elastic lamina located in through there, and here you can see the elastic arteries up through there. And then from the elastic arteries come muscular arteries, and you can see the different elastic tissues still in the wall. They're somewhat, not as elaborate. And then we have arterioles. We still have the internal elastic lamina like we do in the muscular arteries, and that distributes blood. And then we have capillaries. Here we see some cross-section of capillary, a longitudinal view of capillaries, and these are endothelial cells. Lining these, they collect waste and distribute nutrients. And then from capillaries, you go to venules. And the venules have a thinner wall and a bigger lumen in relation to the arterioles. Arterioles have a more defined lumen, scalloped type surface, as opposed to a smooth one and a thicker wall than you have in the venules. So you have an irregular shaped lumen, thin wall, and a large lumen in relation to the thickness of the wall for the venules. And so here we see the veins, they transmit blood, and then large veins transmit blood, and they're a reservoir. And so here we can see in the small veins and large veins over 60%, almost 60% of the blood is in those reservoirs. And that's why you can give blood, because you can pull from these reservoirs. Of course, nature was not set up for us to give blood. It was set up to withstand being cut and bleeding for a while before it clots. And so you don't bleed to death just because you bleed some. And that's because we have this reservoir located. Also note here that only 5% is in the capillaries. So capillaries is where we get the greatest exchange to occur. And of all this blood, only 5% at any given time is actually in the capillaries per se. And here we can see a capillary here with the endothelial cell. You see where it's branched in there, and more endothelial cells there. And we see here the lumen of the capillaries. And so the size or the caliber of the vessel dictates what it is. This is a capillary. You see it's very thin. Compared to that, here's a muscular artery. The wall's very thick and a big lumen, big caliber. And then here's a small vein, a smaller vein, smaller vein, but this is a vein. There's another larger vein in through there. And here, a typical way you see it is a smallest artery and a small vein. Usually they're kind of paired together there. Predominant structure in the wall. What's in the wall? No muscle, a lot of muscle. That dictates whether or not you're a capillary or a vein. The function. If it's blood is going away from the heart, even pumping unoxygenated blood is still the artery, as opposed to coming back from the heart, from the vessel to the heart, would be a vein. So there's different things in the wall. You got the intima. Intima is endothelium. In all cases, blood vessels have to have endothelial cells. That's what touches blood. And sometimes you can have subendothelial connective tissue, and you can have an internal elastic lamina. So all those things make the intima. You would have the internal elastic lamina only on our arterial side. The next one is the media. That's the muscle. So this is smooth muscle layers that go around there. And you can have elastic lamina. You can have elastic tissue in there if you have an elastic artery. And then also you can have the adventitious, which is the connective tissue below. You can have connective tissue in it. So you got intima, media, and the adventitious. Now in large veins, especially hanging veins, here you see the valve in the vein. Not only do you have the circular muscle of the media, but you also have longitudinal muscle in the adventitious. And so this is a longitudinal muscle actually in the adventitious of large veins. So here we see a muscular artery, various layers of smooth muscle, internal elastic lamina, which makes the surface scalloped. And you can see internal elastic lamina, intima, media, and the adventitious. And sometimes these vessels are so large that they have to have other vessels that feed the wall of these vessels. We call that a vasovasorum, as we'll talk about here in a minute. And then if we go to elastic artery, we can see the elastic laminae going through here. So the intima, media, and then the adventitious. Here's a vasovasorum right here. And then this is the aorta of a human. It has the endothelial cells on the surface and a subendothelial connective tissue. This is all in the intima. And then the media, you can see the elastic tissue and the smooth muscle cells, and the adventitious is below. Here in elastic artery, we can see the lumen endothelial cells here, the elastic lamina that goes around the vessel, and this is the adventitious. So the media, intima, media, and the adventitious. Here we see the media again as muscular artery, and the adventitious of those two. And again, we can see the internal elastic lamina and endothelial cells on the outside. So this would internal elastic lamina, connective tissue, and the endothelial cells will make the intima. Here we see the elastic lamina. They are indeed sheets, but they're porous in between, and they'll be touching the smooth muscle cells that are in here. Here's a muscular artery, intima, media, and the adventitious that we have there. And if we look at one with a scanning electron microscopic view, with the adventitious removed, we can see the smooth muscle cells surrounding the intima. So this is the media, cells of the media. If we look at a small artery or arteriole, we see the intima, media with the muscle, and then the adventitious, and we still have elastic lamina and internal elastic lamina. As you can see, intima, media, and the adventitious. As we get to our arteriole, say 1 to 3 or so smooth muscle cells around it, we can see the smooth muscle cells, we can see the endothelial cells, and this would be the intima, media, which is small, and the adventitious out here. Now, arterioles vary in their caliber based on whether or not the smooth muscle cells are contracted or not. And here we can see the same vessels. You can see it's the same vessel here, and a chemical was put here to cause constriction. And so constriction occurred here, made it look like this. That's why it's scalloped, because it's partly contracted. And as opposed to, it could be quite stretched and quite smooth if it's extended. So it's a dynamic process, not just stagnant. Again, we have the intima, media, and the advent tissue in either case. Arteriole, we can see one's branched here, and we can see the smooth muscle cells surrounded in the media. So if you have an arteriole, giving rise to capillaries, and they will grow into the venules. A lot of capillaries have pericytes, not a parasite, but pericytes, which are cells that move along the basal lamina inside there to kind of clean it out. And here we can see a pericyte on the outside of the endothelial cell, and they're actually in the basal lamina of the endothelial cells is where you find these pericytes, as opposed to smooth muscle cells, which are located outside the basal lamina of the endothelial cell. So we see a little capillary in through there. Here's a venule, very thin walled, as you can see. Also, the venule is a source of edema, and you can see where the endothelial cells are separated here. Fluid could be running through a platelet trying to clog up the hole, and a red blood cell is squeezing through this opening, and of course fluid would be coming through with edema. And here sits a pericyte in the basal lamina. There's a basal lamina right in there of the endothelial cell. And so we have arteriole, then capillary. You see a longitudinal view, a cross-sectional view, and the venule. That's your typical. From the venule, we can see a little bit of muscle layer in the media, intima, and a fairly large advent tissue, and it has a large lumen in there. And you can see the smooth muscle cells in the media is very thin, and we see nerve, which is be responsible for the contraction of those smooth muscle cells. So if we compare a venule to artery, you can see there's many more smooth muscle cells surrounding it than you have in the venule. And so remember here the different components that we have in there. In a small vein, you start picking up some of the elastic tissue, and here we can see elastic tissue here, here, and here. So these are elastic fibers, not necessarily elastic lamina that you see. And then when you get to large veins, here we see a large vein here. You have, this is the media, and you have longitudinal muscle in the advent tissue. So we have a little bit of intima, media, and the advent tissue. And this is a small vein here. Here another large artery, and these are veins of different sizes. And this one, you can actually see the valve in the vein that we'll talk about later on. Now, can you name these vessels? Multiple layers of smooth muscle, Venous wall, scallop surface, interelastic lamina distinct. That would be a muscular artery. And these arterioles, one to three layers of smooth muscle around the endothelial cells. These are arterioles. Venules, large lumen, thin wall, smooth surface, venules, and then these are capillaries. The smallest ones are the capillaries, as you see right in through there. And here's a portal vein and the bile duct. And then if we get to the heart, we see that there's a SA node and an AV node responsible for the contraction of the heart. And here we can see it has valves inside there and directs the flow. But the different layers of the heart is named different things. You have endocardium as opposed to the intima. You have myocardium and epicardium on the outside. So the epicardium would be on the outside. Usually there's a lot of fat associated. Endocardium would be the part that actually touches the blood. And here we remember the cardiac cells have an intercalated disc between the two, where cells are attached to one another at the Z-line. And here again we can see these discs which connects one cell to another cell, and there's gap junctions between these to enhance the communication. Intercalated disc again at the Z-line, and of course you have striated muscle. You have the I band and the A band with a sarcomere being from Z-line to Z-line. Lots of mitochondria in cardiac muscle cells, as you can see there. And also there's a blood vessel, a vasovasorum. And this one has a little pericyte associated with it, and nerve to direct it. Now, you have modified cardiac muscle cells that extend down deep into the ventricles and then back up beside theirs. That's a bundle of His, or the Purkinje fibers. And here we see the Purkinje fibers, modified cardiac muscle cells. Indeed, you can see some myofibrils inside there. There's nerve right associated with that as well. And these cells have a lot of glycogen, and glycogen is removed in the process, and that's why they look white, because it's been extracted from them. They have junctions between adjacent cells, so one cell can communicate with another cell to transmit that message down to the ventricles. So the vasovasorum is a vessel of vessels, and here we can see one here. We can see several vasovasorums there. You can see them here, and the largest vasovasorum would be the coronary arteries that we have here that feeds the blood vessel. Control of the blood flow, as we're going to talk about, tone, is a state of partial contraction. Your blood vessels have too much space inside there to accommodate the amount of blood you have. And so they're in a partial state of contraction, so that the amount of blood corresponds to the amount of space occupied by them. And they do that by contracting the smooth muscle and reducing the caliber of the blood vessels. Here we can see these are smooth muscle cells. You can see the fusiform densities, or the dense bodies there. And this is nerve interacting with this muscle. Now, tone is a state of partial contraction of smooth muscle cells on arteries and veins to reduce the caliber of the lumen. So you're reducing the caliber. This is in a normal state. This is a normal state. But if you cut the nerve that innervates the blood vessels, no longer will they be contracted, partially contracted, and they will swell to the fullest extent. And here you can see how much blood would be in the ear if it wasn't for the tone or the partial contraction to occur. And so basically, this is the typical of what we have to regulate partial contraction, and this is what it would be if it was totally dilated. And so in terms of control of vasculature, we have the arterioles. They're the ones that prevent, that eliminates the pulse in the flow. We have peritubular sphincters. So there's sphincters right in here, right in front of the capillaries, that regulate the flow. Also, there's metarterioles. A metarteriole is like a shunt. If it's not contracted, then the blood will go through there. But if this is contracted, then that will run the blood through the capillary network. So between the arterioles, the precapillary sphincters, and the metarterioles, that regulates the flow coming in there. And the arterial function is allow sufficient pressure for flowing through the capillaries, but low enough pressure not to damage. Remember this, you don't have any muscle in the wall, and so you can't have too much pressure. And so they let some in, and then they reduce it, let some in, reduce it, so they can maintain the nutrient level or whatever. Also, the arteriole has autoregulation. That is, it's self-regulating. In addition to having nervous controlling, it can relax itself. And it does that by oxygen tension. If oxygen tension is low, it relaxes. And when it relaxes, that increases the caliber of there, and you get more flow coming through there, again, to bring in more more oxygen. So it's the smooth muscle cells of the arteriole that has the autoregulation. Here we see arteriole with the endothelial cell and the smooth muscle cell, and here we can see the precapillary sphincters. There's nerve there associated with it. So these guys are radiating through there, and then this is the arteriole. Now, endothelial cells themselves are not just sleeping. They are very active cells. They have enzymes and receptors for transporting things across. Also, they transport without much energy. They're flat, and so you don't make much turbulence as you go through there. And they have a non-wettable surface. It's a negative charge, and it's non-wettable. It's kind of like waxing. So the inside of your blood vessels are somewhat, as if they're waxed, because they don't absorb the liquid as is going through in the cell itself. It brings it in vesicles and transport it, as we'll see in a minute. Now here we see endothelial cells. This is in the capillary here. Here's a little arteriole, a venule in through there, a lymphatic in through there. And here we can see a little arteriole. We got one layer of smooth muscle. Endothelial cells, you will see them kind of flatten as we see there. But if you see an on-face view, you see it's actually wider than what you see on the side. Endothelium, very active cell. And here we can see where it has these transport vesicles. So whatever's inside there, the serum, is transported out to the outside, to the muscle or whatever. There's actually different methods of transport. You have vesicle transport, as we just saw. There's also channels that go through there, between there, and junctions between adjacent cells. Then there's different types of capillaries. There's continuous capillaries, and that's what we have in muscle, testis, brain, thymus, and the basal lamina is complete. There's also fenestrated ones, and this is what we have in the adrenal, and we have in the corpuscle of the kidney. So we have it in the glomerulus and adrenal. Then they have a discontinuous or the sinusoidal. That's what we have in the liver. And the basal lamina is incomplete or even lacking. And then you find that in the liver, spleen, bone marrow. These are places where in the liver you want to bathe the hepatocytes with the blood. So you bathe it with a serum of the blood by having these big holes in there. But you have the hepatocytes preventing any leakage occurring there. In the spleen, that spleen gets rid of red blood cells. So you take cells outside the bloodstream and they have to squeeze back in. So you have to have a certain amount of space, discontinuous ones, so the cells can come back in. And then there's a bone marrow. The blood cells are produced in the bone marrow outside the blood vessel. It has to get inside the blood vessel. So therefore you have to have capillaries that will facilitate blood cells entering the bloodstream. Now here we can see a continuous capillary, which you can get diffusion of nutrients, oxygen, carbon dioxide can go out through there. So you can get the diffusion of those. You can get things from the channels. You can get things through receptors, receptor-mediated type transport. And so this is a continuous layer. You don't have big gaping holes in it. This is fenestrated, where you see the endothelial cell pinches down to a little small layer for fenestra, and that facilitates a lot of fluid coming out. And then there's sinusoidal, where you got gaping holes. So this is a hepatocyte, and so these are endothelial cells here, and so fluid can actually bathe the hepatocyte. Usually fluids is confined by the endothelial cells, but in the liver, they actually bathe the hepatocytes. And here we see a continuous capillary, one like you see in the testis. So we see it continuous there. The endothelial cells are continuous through there. You can't have swelling of the testis with a capsule that you have. The fenestrated one, adrenal, this happened to be in the kidney, in the corpuscle, that's here. So you have it between the endothelial cells. These are endothelial cells, have fenestra, and then there's podocytes right outside there. Here we can see the fenestra, varying sizes, and here you can see where this would be where the endothelial cell is swollen and thin, swollen and thin, swollen and thin, kind of like what we see here. And so that's what we're seeing there, the fenestra. The other one is sinusoidal, and this is where you got gaping holes. So you can see the hepatocytes below because you can look through the hole of a thing. And you can see hepatocytes inside there. There's some more hepatocytes that you can see right there. So the blood serum bathes the hepatocytes. So these are the endothelial cells. These are hepatocytes. So fluid actually bathes the hepatocytes that we see there. And so here we see the blood in the heart, liver, and in the kidney. In the gut, you have blood vessels growing, but when you have these type with anastomosis on there, oftentimes blood vessels start independently and then they fuse together, like these, especially sinusoidals. They start to develop, and then the lumen fuses together, as opposed to a blood vessel just sending out a projection, as we'll see a little later, and causing a blood vessel to develop. In fact, this is what we're seeing right here. So this is your typical blood vessel development, where the endothelial cell sends down a pseudopodia, and then you have cells dividing through there, and then you have spaces, and then that space becomes continuous, and all of a sudden you got an outgrowth of blood in through there. The mesenchymal cells are the cells that are the source for endothelial cells. They're the precursors to muscle cells, smooth muscle cells. They are the precursors to fibroblasts. And all those three things is what we have in a blood vessel. We have endothelial cells in the intima. We have muscle in the media, connective tissue in the adventissue. Here we see angiogenesis, or the growth of blood vessels. This is 60 hours after wound healing. You got major vessels here, and you have budding of new vessels as you get spaces being developed into here, and growth of the projection, and then finally the lumen is continuous, and you start blood flow through and through there. Another interesting thing about blood vessels are valves, and you have that in medium caliber veins, especially extremities, and also the collecting and lymphatic ducts. And this is a lymphatic duct here. You see the endothelial cells lining it like those of the endothelial cells that line the blood vessels. The purpose of the valves is to ensure unidirectional flow. And so it doesn't flow backwards. You want the blood to flow toward the heart. And here you can see where red blood cells have been trapped by preventing backward flow in these veins. Now, the valve is really composed of endothelial cells. We see the endothelial cells here on both sides of this valve. You have endothelial cells draped over connective tissue. That's what a valve is. Here we can see in a vein, you can see the valve in through there, endothelial cells draped over connective tissue. Now, of course, the purpose of the valve is to have unidirectional flow, and this will make the flow go in this particular direction. You also have valves in the heart. This is a tricuspid valve in the heart. You can also have two components of the valve, too, depending upon where it is. And you can replace the valve, artificial valve, if that's the case. But here we see the valves in the heart. Now, when the blood first starts going through the heart, it goes straight, then curves, then coils, and now it changes directions several times in the course of the go. In terms of microvasculature, the common thing is to have an arteriole, capillary, and venule. But there's also shunts. I mentioned to you the metarteriole is a type of shunt, and that will let a larger caliber lumen it can have, and so the blood can go around through and not go through the capillaries. Also, there's an AV shunt. And an AV shunt, arteriovenous anastomosis, where blood can go right through there very quickly. And so a couple of places you need that is one in the penis for the erection, also in your skin. If you blush when something you get embarrassed, it's because blood has gone through this shunt and has been a big plexus of the venous plexus that has shunted through blood faster than it normally would. So that's the AV shunt. There's also portal vessels, and the portal vessel could be vein or it could be arteriole. And if it's arteriole, one example of that is in the kidney. You heard of afferent and efferent arteriole, right? Well, the first capillary network is in the glomerulus, and the second capillary network is in the peritubular capillaries. And the vessel in between, the so-called portal vessel, is a portal artery, as opposed to other places it may be a portal vein. And so the purpose of the portal system is to have modified local blood composition. That's what it does. Local is very important. So it's between the first capillary network and the second capillary network. That local connection there is very important. And it modifies the blood. In every case, the first capillary network modifies the blood, picks up hormones, reduce the amount of fluid in there, keep the osmotic pressure, whatever. And then the second capillary benefits from that, as we'll see here in a minute. So in the case of a kidney, you have the afferent, efferent arteriole. So the efferent arteriole is a portal arteriole, and that carries blood to the peritubular capillaries. So you got a lot of fluid coming in. The fluid goes out in a filtrate into the Bowman space, and the solids stay back. So you have high osmotic pressure in here, which sucks the fluid right back into your capillaries. That's how it works in the kidney. Now, in the case of the hypothalamic pituitary axis, you have releasing factors released in the first capillary network up in the hypothalamus, and that goes through portal veins in through here to a second capillary network, which is in the pars distalis. And so the first capillary network picked up the releasing factors, in other words, modified blood composition, and then the second one used that blood composition modification, the releasing factors, to cause the pars distalis to secrete its hormones. There's also barriers. You don't want blood everywhere. There's a blood-brain barrier. You've heard about that. That's a occluding junction between endothelial cells. There's a blood-thymus barrier, which is really in the cortex, and that is occluding junctions of endothelial cells, and also a sheath of reticulum cells, that we'll see in a minute. And then there's a blood-testis barrier, no counterpart to this in the female, and that's occluding junction between Sertoli cells. So this is not the occluding junction of endothelial cells, but it is between the Sertoli cells and the seminiferous tubules. So here we see in the brain, for the brain barrier, this is your typical capillary with a marginal fold that protects that junction, just a little fold there. But in the case, and here you can see where the typical junction, this is typical. But in the blood-brain barrier, that marginal fold is glued down. And so the tight junction there, so this is glued to that. And so the tight junction is thicker in the blood-brain barrier than it is elsewhere. In the blood-thymus barrier, not only do you have endothelial cells, which you can see where they have stopped the electron opaque substance, anything got through, the reticulum cells ate it up. And so you have two components to the barrier. But in the case of blood-tested barrier, it's the junctions, tight junctions of the Sertoli cells above the spermatogonia. And here you can see where lanthanum nitrate can penetrate around the spermatogonium, which is outside the barrier, and stopped abruptly at the Sertoli cell junctions, keeping the primary spermatocytes and spermatids and sperm away from the immune system. And so here we see lymph vessels. They collect fluid. So you got arteriole coming in through there, blood coming out of the capillaries, going right back into the venules, and what doesn't go through the lymphatic system to be returned through the thoracic duct back to the bloodstream. So the function is to return protein, fluid, and blood cells back to the bloodstream. Transport secretions, hormones, antibodies, and also fat, neutral fat. It's in the central lacteal of the intestinal villus that you get fat reabsorption, and that fat reabsorption goes back through the thoracic duct into the bloodstream before it gets to the liver. And that's the problem with fat-soluble toxins, because the fat goes through this route. The other things go through the liver to be cleared, but a fat-soluble toxin will be exposed to your brain and various parts of the body before it gets to the liver. And so the lymph vessels themselves, very thin walled, very, very thin walled, and they have little anchoring things that kind of holds them out. They're composed of lymphatics, muscle, pulsating, things like that is what makes them flow. Unidirectional flow, it's controlled by valves. You have valves in the lymphatic vessels, and the rate is remarkably fast. You can see a lymph node. There's a lymphatic vessel there and a lymph node, and it has anchoring devices that hold it open, as I mentioned to you before. Here we see a little lymph vessel. The endothelial cells are thinner than what we have in our capillaries. Endothelial cells. There are disease states associated with it. Arteriosclerosis is where your elastic lamina, hardening of the arteries, is replaced by other connective tissue components that doesn't stretch, and so the artery can't stretch in that case. Atherosclerosis is a patchy, irregular heart attack, intima, stroke, things like that. So you're clogging up the plumbing. And here you can see one of those plaques that is in there that could restrict the flow. They can come in there with a laser scope and cut that. They can also expand this to push that plaque back and open it up. And here you can see, this is actually my heart back in 2002, and you can see it's about 90% constricted area there. But after the stent, you can see that the lumen is very open in through there. It was constricted and then open. So in summary, the blood vessels are adapted for mechanical factors to resist the pressure, and metabolic factors, even has some parasitic venules in through there, increase elastic tissues, go back, but you have major elastic tissue coming right out of the heart. And so it's adapted to withstand the pressures of the heart. There were several books we used and samples of body worlds, thanks to them, where we used illustrations that came out of the book. I don't want to take credit for any of those. I didn't make any of those. I did take some pictures, but the original source of these illustrations that you saw are from these textbooks, and we thank them. Next time we're going to talk about overview of the immune system. Either that or we're going to go to Rio de Janeiro in Brazil. They got a chairlift to go up to there, and we rode all the way up to the top of there, and we had to hang around this beach house for 3 or 4 days. It was tough. Thank you, guys. Hope this was useful to you. If it is, please share it with your neighbor. Hi, I'm Larry Johnson, a professor at Texas A&M University, and good luck with your studies.